Well, hi guys, welcome back. Oh, give me 1 second. Okay, okay. There's a lot of feedback. Okay, let me find out what's going on here. How about now? Is that a little better? Okay,
Yeah,
good.
that's better.
Yeah, I was joined. I joined with my cell phone so I can make sure that uh, I see what you guys see. So hopefully everybody sees chapter 3. Okay. All right. Well, welcome back, guys. Looks like we're almost done with the first week. I sent out reminders concerning all the assignments. So, some of you are knocking them out. That's great. But I just want to make sure that you don't get all flustered toward the end of the week and try to get them all knocked out, in one day. So, try to do as many as you can. We do have that first quiz on Monday, which is over these chapters 1 through 3. It will open up. All the sections are taking the quiz the same time. So it opens up at 8 o'clock in the morning and it stays open until 10 p.m. Okay, you got 60 minutes to do it and 1 attempt. So make sure you set some time aside so you can be able to complete that. Okay. Well, let's jump into chapter 3, and here where we talk about unit conversions and so forth. Now, we introduce this for a particular reason. There's a technique that we utilize to help you to convert from one unit to the other. And that particular technique, we want you to be able to use the same technique when we get into chemical reactions. And basically, you're setting up your problem such that the units cancel out as you do the mathematics. Okay. And if you set it up properly, you follow your units, you should be okay. Now, I briefly talked about this with respect to the metric system. Uh, we use the units of meters for length, grams for mass, and liters for volume. And in this table here, you have in the far right the respective symbol for those. We Seconds is utilized either both in the English units and the metric units, and that has the letter S. Okay. Now, I also sent you a file that kind of broke down the symbols for the prefixes, the kilo, the deci, the centa, and the milli. Okay. So here in this case, the kilo prefix is the symbol K, which is 100 times larger. So meaning that 1 kilogram or 1 kiloliter or 1 kilometer, there are 1,000 of the respective gram, meter, liters. Okay, deci is the prefix for 10 times smaller. And one way to remember that, 10 years in the decade. Okay. C for centi, or 100 times smaller, 100 years in a century. And M for milli, which is another way to say it to help you remember. In 1 millennium, there are 1,000 years. Okay. And then the new one we introduced looks like a letter U. That's for micro. And that is a million times smaller. That being the case, if you're asked the question, well, and 1 meter is equivalent to 100 centimeters. Okay. You see the unit CM, it tells you 100 century, 100. Go to the next one. 1 meter is equal to blank decimeters. That must be 10. And 1 kilometer is equal to 1,000 meters. 1 meter, there is a million micrometers. And in 1 meter, there are 1,000 millimeters. Okay. So keep track of, you must be familiar with these. And these are, again, are ratios that you can utilize when we start doing calculations. Okay. So, for example, we utilize what's called the factor label method. Okay. Other names that they utilize called dimensional analysis. Simply put, it's keep track of your units. Okay. So you're given the problem, identify the units that you're trying to determine. What are the units of your answer? That would be the first step to figure out how you're going to get there. Identify what you're given. The problem gives you X amount of whatever factor. Identify what you are given. That's your starting point. Okay. And then from the starting point, you're going to introduce or use factors written in parentheses such that you set up those factors such that the units cancel out to eventually get to the units that you are looking for. Then it's a matter of just plugging in the numbers in the calculator and you have the answer. Okay. Check your units. Okay. And then finally at the end, depending on your sig figs, you round your answer off for the proper number significant figures. Okay. Now, first of all, when you set that problem, don't just arbitrarily throw in that conversion factor. First, determine how you're going to set that conversion factor. Which units go in the numerator, which units go in the denominator. Okay. Sometimes you have to, like some of the problems are we created for the activities. Show your units. If you want to get full credit on these activities, so show me how you did the work. Okay. For example, let's take this one here. It says how many liters are in 2,389 milliliters. So what are you given? You're given 2,389 milliliters. Okay. So I write that down. Then they're asking you how many liters. So what you're searching for unit-wise is liters. So I need to go find a conversion factor, which is, I know that in 1 liter, there are 1,000 milliliters. So I set that conversion factor. Notice that my milliliters will cancel out. Milliliters divided by milliliters cancel out, leaving me the units liters. And now it's a function of doing mathematics. So taking 2,389 divided by 1,000, then your answer is 2.389. Now think about the answer that you get. Okay, you're dividing 2,000 by 1,000, and so your number is going to be smaller than what you started off with. Okay, and so when you look at your answer, just don't look at the calculator and say, "Oh, that must be correct." You may inadvertently push the wrong button, or instead of dividing, you may have multiplied the number. And so give it some thought with respect to the answer. Does it make sense mathematically? Okay, based on what you're doing. There's another example. Now here, they're asking you how many kilometers are in 12,300 in centimeters. 12,300 centimeters. Okay, so we need to convert centimeters to kilometers. All right, so we write down what we have, what we're given. All right, I'm going to need factors to get me to kilometers. And so I know that in 1 meter, I have 100 centimeters. So I put 100 centimeters in the denominator for the first factor. Why? Because my units will cancel out. Okay, where is it? Drawing. Okay, you can see here that centimeters cancel out. So that leaves me with the units and meters if I were to stop the calculation at this point. Okay, but I'm asked to go to kilometers. That's the problem. So I need one more factor. And I know that in 1 kilometer, I need a factor that will cancel my meters. So my next factor will be that 1 kilometer is equal to 1,000 centimeters. So I set that problem up. I check my units, okay? And then I realize, okay, I'm dividing 12,300 by 100 and 1,000. So that number that I'm going to get is going to be a lot smaller than the number that I started off with. Where is my, oh, I know, there it is. And so I get 0.123 kilometers, okay? So if you're setting up your problems with these factors, checking the units, and now do the math, and then look at the answer. Does that answer make sense based on the mathematics that I did? Now, these factors that we're doing here, this is later on down the road when we start with chemical reactions. You may have 3 of these. If I start with compound X and I want to figure out how many grams of compound D, I'm going to need conversion factors. And I'm going to set these up, and I'm going to do the same process as far as setting up my units so they cancel out properly. Okay. With respect to English units, these are on you. Like 2 cups to 1 pint, 2 pints to 1 quart, so on and so forth. We supply the conversion factors from going from English to units, actually, English to metrics. And so those are available in the shapes table. So if you haven't done that yet, download and print out that shapes table, because you have a lot of factors in there that you'll eventually use. Also download the periodic table, because we're going to be using that quite a bit. All right, I showed you this already to kind of help you out with cups and pints and quarts. Okay, kind of visualize that picture. In 1 gallon, there are 4 Qs or 4 quarts. Within 1 quart or 1 Q, there are 2 Ps or 2 pints. And within the pints, there are 2 cups. Those are my conversion factors to get me from cups all the way to gallons. Okay, so in this example here, they're asking you the question, how many gallons is 44.5 cups? Okay, 44.5 cups. So I write down what I start off, what I'm given. Okay, and so I got cups. I need to get to gallons. So I use my little symbol here. I know that there are, in 1 pint, there are 2 cups. Notice that I put cups in the denominator. Why? Because I want cups to cancel mathematically, leaving me with the units pints. We're not at what we're looking for. Does a 0, which Sonia, you said you asked the 0, which 0 are you asking about?
It was for the problem that we did when we converted the 0.123. I just want to know, would it be wrong if we just put 0.23?
Oh, that
or
one right there?
Significant? Yeah.
Oh, no. By convention, yes, they put a 0 in there. If you write 0.123, that would not be incorrect. We try to anticipate that as far as the answers in Canvas, that a person would forget the 0, but that's okay. You will not be incorrect if you forget the 0.
Okay, thank you.
Okay, all right. And so we're at 1 pint to 2 cups. So it gets me to pints. From pints, I want to get to another units because eventually I want to get to quarts, right? So I know that in 1 quart, I got 2 pints because I know that factor there. Uh, so here, my pints cancel, my cups cancel, leaving me in quarts. I'm not at the gallons yet. Okay, so I need one more factor. I know that they're in 1 gallon, there are 4 quarts. So now I set that up. Okay, I check my units. My units all cancel out, leaving me with gallons as my final unit. So that tells me I got the problem set up properly. So now it's a matter of the mathematics. Units all cancel out. I'm good to go. Keep track of my sig figs. Now these numbers 1 and 2, 1 and 4, those are exact numbers. Remember we talked about exact numbers. So they would not play a factor in sig figs. So you start off with 3 sig figs, your answer should have 3 sig figs. Okay. Now one question I have a lot is, well, can I not combine all of these factors in the center to make one factor to get me directly from cups to gallons? Sure you can. You can do that. I put them out separately here, but anybody know how many cups are there in 1 gallon based on what you see up there? Anybody want to take a guess? Don't take a guess. Look at the factors that I put up on the table there on the slide. If I wanted to make a whole new conversion factor, how many cups could I say? How many cups would be in 1 gallon? 16, exactly. See, because if you look at just those 3 factors in there, the quarts cancel, the pints cancel, leaving me behind 1 gallon per cup. Okay, so 4 times 2 is 8, times 2 is 16. So there's another factor right there you can use, and that factor would be fine. Okay. All right. Next question. How many inches in 3.5 yards? Which reminds me, a lot of people, for whatever reason, use a conversion factor that in 1 meter is equal to 1 yard. That is incorrect. Okay. It is 1.09 and some other numbers. So I don't use that conversion factor. 1 meter is equal to 1 yard because again, that is incorrect. How many inches in 3.5 yards? Okay. So we write down 3.5 yards. Okay. I know that in 3 feet is equal to 1 yard. So I get my first conversion factor. Okay. Then I know that there's 12 inches in a foot. I set them up in a manner so my units can cancel out because I want to get 2 inches and there I am. My yards cancel, my feet cancel, leaving me the units of inches. And so now I will do the math. Okay. And 12 times 3 times 3.5 gives me 126 inches. Now, would that be correct to display that answer in that form? No. Why? Because the 6 significant figures. Okay. 3 feet in 1 yard, exact number. 12 inches in 1 foot, exact number. And so the number that defines our sig figs is 3.5, which has 2 sig figs. So we need to convert 126 with 2 sig figs. We go to the number 2, which that's the 2 sig fig position. We need to determine, does that 2 remain 2 or go up? We look at the neighbor is 6. That means that the 2 becomes a 3. Okay. And so our answer with the correct significant figures is 130 inches. Okay. Check my units, everything cancels out. And if you want, you can make from those 2 conversion factors, 1 conversion factors to say that there are 36 inches in 1 yard. And that's perfectly okay to use if you recognize that. Okay, now in the shapes table, we give you these factors. That 1 inch is 2.54 centimeters. 1 pound is 454 grams. 1 quart is 946 milliliters. Now, of these conversion factors, the 1 inch is 2.54 centimeters is treated as an exact number. Therefore, would not be a factor with respect to sig figs. The other one, 454 grams and 946 milliliters, are approximate. They're measurements. Okay. Excuse me. Therefore, they could play a factor in the sig figs. Okay. All right. So remember those. Only the first one is treated as an exact number, and the other two are approximate, and it could be a factor. And yes, you're given these when you're taking exams or quizzes because it's in the shapes table. All right, how many pounds are in 248 grams? Well, we write down what we're given, 248 grams. Our conversion factor is that 1 pound is equal to 454 grams. Okay, and so I set it up in this manner, and my units of grams cancel, giving me pounds. Okay. Now, in both cases, the 454 is an approximate number in measurement, so that's 3 sig figs, but our number given is 248, which has 3 sig figs, so our answer should have 3 significant figures. Okay? Remember, multiplying and dividing, we look at sig figs. Adding and subtracting, we look at decimal places. Okay, decimal places. Next example. How many inches are in 3.54 times 10 to the negative third kilometers? Okay, kilometers. All right, so we may have to use some scientific notation here, or you can take that number and convert it into a decimal number, moving the decimal point to the left by 3 places, okay? Or use your calculator with the scientific notation. So the first setup, we're given 3.54 times 10 to the negative third kilometers. Well, here's my first conversion factor because I want a factor that gets rid of kilometers. Well, I know that in 1,000 meters, that is equal to 1 kilometer. So that takes care of the kilometer units, okay? So my kilometer units get taken care of here. Now, I'm not where I need to go because I need to go all the way to the units of inches. Okay, so I need another factor to get rid of meters and eventually get to inch. But I could go directly, but I know that in 100 centimeters, let me restate that. In 1 meter, there are 100 centimeters. So I got another factor here. Okay. So I'm getting close now because now I know from my conversion factor in the shapes table that in 1 inch is equal to 2.54 centimeters. So I put my unit next factor here. Okay. I double check my units. Everything's set up properly. Everything cancels out, leaving me my final units in inches, which is what I'm looking for with respect to units. Now the math is on you. 3.54 times 10 to the third times 1,000 times 100 divided by 2.54. Now, I've been asked this question before as far as your calculator. Okay. Some people say, well, ask me, well, if I take 3.54 and I multiply by 1,000 and then by 100, and then I write that numerator down, then I divide by 2.54, do I get is that the correct way to do this on my calculator? Well, the answer is this. It depends on your calculator. Your calculator, most calculators understand the mathematical function. So if you were to take 3.54 times 10 to the negative third and divide it by 2.54 and then multiply by 1,000 and multiply by 100, you should get the correct answer if the calculators function like it should be. But to check, do this. Take 3.54 times 10 to the negative third, divide by 2.54, and hit the equal sign. Then multiply by 1,000, then hit the equal sign. Then multiply by 100, then hit the equal sign. Note your answer. And then go back and do the same mathematical function without the equal sign and see if you come up with the same answer. The answer with the equal sign is correct because your calculator did the mathematical function and it waits for the next thing. Okay, so be careful with your calculator. If it's not set up properly as far as the rules of mathematics, they may give you the incorrect answer. All right, let's clear this up. All right, the next question is how many 2.0 liter soda bottle contains how many quarts? Okay, so I'm given 2.0 liters. All right, I have the conversion factor that 1 quart is equal to 946 milliliters. That's given to you. So that puts me in milliliter units. So I need to convert my liters to milliliters. So that's where my first factor comes into play, where I have 1,000 milliliters per 1 liter. Okay, my liters cancel, and then I put in the second conversion factor that there is 946 milliliters in the quart. Check your units. Okay, and do the mathematics. Notice remember that 946 is an approximate, but it has 3 sig figs. But the problem gives me 2.0 liters, which has 2 sig figs. So my answer should have no more than 2 significant figures. Okay, so my answer is 2.1 quarts in 2 liters. All right. Sometimes you might be tempted to get conversion factors and go Google them. Be careful. Sometimes the factors are not 100% correct. So just use the conversion factors that we give you as far as digits, which also brings me to the point. Eventually, we're going to talk about from the periodic table the atomic weights of these elements. Again, use the atomic weights from the periodic table that we give you. If you Google them, sometimes they will give you some crazy numbers up there. And our answers are based on the factors that we supply. Okay. All right, we're going to change gears a little bit and talk about volume by displacement. Okay, and this is pretty self-explanatory. You're in the bathtub. You haven't jumped in yet, but you see you're getting ready to jump in the hot tub, right? As you get in, you have an X amount of volume. As you totally immerse yourself into the hot tub, the volume go up? Yes, yeah, it does, right? Just hot tub or bathtub. The volume goes up because your volume displaces an X amount of volume in that liquid. Keep that in mind if you do the extra credit, because in there you are immersing blocks, and you want to immerse those blocks that when you get to that extra credit completely, because you want to get a volume. And what you're looking at is the difference of volume of where it started, of where it ended volume-wise from where it started. Okay, so for example, here we took a diamond, we put it into a cylinder containing water. It contained 20 milliliters of water, and as you dumped in the diamond inside the ring, the volume went up to 34.7. Now, the diamond did not displace 34.7 milliliters. Okay, it did not displace that. What it displaced is the difference of where it started at 20 and where it ended. And so the volume of the diamond here is only 14.7 milliliters. Okay. Now, why would we want to do this? Because we would be talking about density. And density, if you recall, I did kind of touch on it, is the ratio of mass over volume. And normally, if you have a nice straight box, you can calculate the volume by measuring. But if you have something that has an irregular shape, best way to do it is dunk it in some kind of liquid and measure the displacement of the uh, of the uh, uh, of the material, the displacement of the fluid that this material, whatever it is you're trying to determine the volume of. Okay. Uh, and question here: diamond is made of carbon. I mentioned that before, and it's a solid. All right. Now, how do we calculate the volume of just say a box? Okay. Recall the equation for volume, that is length times width times height, not to be mistaken with area. Area is just length and width. Okay, that's 2-dimension. Volume is 3-dimension. Okay, length, width, and height. And so if we're given a shoebox with these particular measurements, 24 centimeters by 11 centimeters by 16 centimeters, okay, we can calculate the volume and also keeping track of your units. Centimeters times centimeters is centimeter square, times centimeters is centimeter cube. And if we had another centimeter, it would be centimeters to the 4th power. And if we have another one after that, centimeters to the 5th power, etc., etc. Okay. Our answers are problems 24, 11, and 16. I should say the numbers given have 2 sig figs. So our answer should only have 2 sig figs. Okay. So that brings us to density. Density is simply the mass per volume. Every matter, all matter has density. You have density. You have a mass and you have a volume. You know, the mass we can easily determine. We just weigh you. The volume, we can probably dunk you in some big tank and measure the volume that you displace. We can calculate your volume. Okay. So that's that ratio, mass over volume. Keep this in mind. It's another ratio. We can flip, write it as volume over mass or mass over volume if we need that density to do calculations. Okay. Generally, the units that we utilize is grams over cubic centimeters or grams over cc's. And we know that in 1 cc is equal to 1 milliliter, so it's grams over milliliters. The most common units are grams over milliliters. Okay, so just think of matter, the density is how much matter is in a given space. Right? So that being the case, what state of matter will be the most dense? And that would be a solid. Okay, solids are a lot more dense than, say, gases. Gases, not very dense at all. The density of water, for example, that's our reference point. Water is 1 gram per cubic centimeter or 1 gram per milliliter. Okay, where density is their density of gases are much, much smaller. And heavy metals, you know, in this example, gold, 18 grams per cubic centimeter. Okay. Again, these are ratios. These are constants of physical properties of whatever material you are studying. So we can do density calculations. The type 1 calculation, the first one is simply you're given the mass, you're given the volume, you can calculate the density. Okay. Or if you're given the density of a material, you can calculate the mass and or the volume, depending on the question being asked. For example, chloroform is a chemical that used to be used in the old days when you had an operation. They would knock you out for the operation. They'll put that liquid in your face and knock you out. Okay, before the new anesthesias are out, that's what they used to use. But it has a density of 1.48 grams per milliliter. Now think about that unit, that ratio for a second. That means if I measured 1 cc or 1 milliliter of chloroform, it would weigh 1.48 grams, okay? Or vice versa. If I were to weigh out 1.48 grams of chloroform, it would have a volume of 1 milliliter, okay? Now, if I had 2 milliliters of chloroform, how much you think that would weigh? Who could answer that? Okay, I got 2 milliliters of chloroform. How much would it weigh? Go ahead, type it in or unmute yourself if you like, and you can tell me. Two milliliters of chloroform. How much would it weigh? Nobody want to give it a shot? It's right there in front of you. Think about it. If 1 milliliter weighs 1.48 grams, how much do you think 2 milliliters would weigh?
So would you time the 1.48 by 2?
Exactly. Okay. So there'll be what, 16 and 9, 2.96? Exactly. And if you had 3 milliliters of chloroform, it's 3 times that weight, right? Okay. So that being a ratio, again, you like every ratio I've talked about so far, be it density, be it dollars per hour, be it miles per hour, it can be written in one or two ways, with the grams in the numerator or the milliliters in the numerator. And we can use that factor to either to multiply it with whatever number we're given. So if we're looking for grams, starting with milliliters, we use the factor on the left. If we're looking for milliliters starting with grams, we use we write the factor as written on the right hand side. Okay. For example, let's do the first type of example. The question here says, I got a necklace. It weighs 484.56 grams. And they give you a volume of 25.64 milliliters. They simply want you to determine or calculate the density. Okay. Well, we know the density is mass over volume. You're given the mass, you're given the volume. It's a matter of plugging the numbers in and doing the mathematics. Okay. Keep in mind, those units don't cancel out. I got grams in the numerator and milliliters in the denominator. They're unlike units, so that they go along with the answer. Those are the units of density. Okay. We have 5 sig figs in the numerator, and we have 4 sig figs in the denominator. Therefore, our answer should have no more than 4 sig figs, which is 18.90 grams per milliliter. That is the density of that particular necklace. Okay. All right, so we're going to do the second type of problem. Okay, the first one was simply a straightforward calculate the density. Here we go back to chloroform, which had a density of 1.48 grams per milliliter. They're asking you the question, how many grams would 17.5 milliliters of chloroform mass? Basically, if you measured out 17.5 milliliters of chloroform, how much is it going to weigh? The density is a pretty good physical property to have. Why? Because if you have means to actually have a balance to weigh the chemical, if you know the density, but you have a way to measure it, if it's a liquid, to measure its volume. Once you know the volume, you know the weight based on the density. Okay, so we write down what we're given, 17.5 milliliters. Our conversion factor is 1.48 grams per mil, but no, not here. We want the milliliters in the denominator. Okay, why? Because we want milliliters to cancel out. Because the question is asking us how much does 17.5 milliliters weigh? So our units should be in grams or some units of mass. Okay. So we do the math, and it weighs 25.9 grams. So 17.5 milliliters of chloroform will weigh 25.9 grams. Okay. Second question, they're asking you, how many milliliters would 0.0735 grams of chloroform occupy? So in this time you have a balance, so you actually weigh out the chloroform. Now you want to know, okay, what is its volume? And so we write down what we're given, okay, and we're looking for milliliters. We want the volume because that's what the question asked. So we write the conversion factor, we invert it, we want milliliters in the numerator and grams in the denominator, okay? And now you simply do the math, grams cancel out, leaving us with units of milliliters. So 0.0735 grams of chloroform would have a volume of 0.0497 milliliters, okay? With the correct sig figs, 3 sig figs. Okay. We're going to shift gears a little bit. We're going to talk about temperature. It's kind of related to energy. Okay. But here it's pretty self-explanatory if you think about it. You know, hot molecules move very fast. Think about it. You're in the beach, 100 plus degrees out there in the beach. You're walking across that sand. Do you think you're going to walk very slowly? It's hot. You're going to run. Okay. Because it's hot. So the same thing with molecules. If they're warmed up and they're hot, they're gonna move fast because they have a lot of energy, high energy. Okay. Now, cold molecules, the fact that they're cold, don't have a lot of energy, so they're moving around slowly because they have low energy. Okay. Now, that doesn't mean that the temperature, all the temperature is a means to measure the amount of, well, how can I state this? Temperature does not measure energy. It's just measuring, the thermometer just measuring the temperature of the molecule. We know the higher the temperature, the more energy you have into the system. That's all you can say. Okay. So temperature is just simply measured by a thermometer. We have 3 scales that we work with, mostly the Celsius. Okay, but this is a relationship between Fahrenheit, which most of the world, well, I mean, the US and UK and some other countries utilize as far as temperature, Fahrenheit. But the countries that use the metric system use Celsius. Okay. Now, the units of Fahrenheit and the units of Celsius, they go to infinity. So the scale going up on the up direction, that's supposed to be an arrow, or the down direction goes to infinity in both the Fahrenheit and the up in that way and up in this way, they go to infinity in both of them. Okay. Kelvin does not. Kelvin will end up with 0 down here in the bottom. 0 degrees Kelvin eventually. And now that temperature is what we call absolute 0. That's when all matter stops moving. We haven't reached that stage yet. Kind of close, but we're not there yet. Now, at this particular temperature, 212 degrees, that corresponds to 100 degrees Celsius. Now, to get to Kelvin, all you simply do is take Celsius and add 273, okay? So 100 plus 273, guess what? You get 373. 0 degrees, that's the freezing point of water, which is 32 in Fahrenheit. and that corresponds to 273 in Kelvin. Okay, so those are the three temperature scales that we utilize. And I mentioned absolute. Absolute zeros, really absolute is Kelvin. That's when all matter stops. You have the conversion factors here. You really don't have to memorize them. Why? Because they're in the shapes table. So if you want to calculate Celsius or Fahrenheit, you take Fahrenheit, subtract 32, divided by 1.8. That gives you the temperature in Celsius. If you have Celsius, you want to go to Fahrenheit, take Celsius, multiply by 1.8, and then add 32, and you have Fahrenheit. And Kelvin, you simply add 273 to Celsius. So if you're given the temperature in Fahrenheit, and you need the temperature in Kelvin, you first convert it from Fahrenheit to Celsius, and then you add 273. And that's what this problem says here. Phoenix can get up to 115 Fahrenheit. What is this in Celsius, and what is it in Kelvin? And you might plug the numbers in, and you should come up with 46 Celsius and 319 Kelvin. Okay. Which brings us to heat. Okay. So heat is just a measure of the total energy of atoms. They asked this question here when I first saw this. I'm like, what? Kind of did a double take. It says, which of these two beakers has a higher temperature? Well, if you look at the thermometer, they're both reading 100 degrees Fahrenheit. So obviously they both have the same temperature. Okay. So that implies it must be the same chemical. Because whether I have 1 milliliter of water, for example, or 10 billion milliliters of water, it's going to boil at the same temperature. Okay. So now the question is, which has the greater amount of heat? The one in A or B? Well, one question to ask yourself is, if you're boiling, say, a cup of water as compared to a pot of water, and if you were to spill it, which one would you rather have to spilled on you? The cup of water or the big pot of water for spaghetti, for example, boiling? Obviously the small. Why would that be the case? Well, because there's less molecules in the small pot of water compared to that big old giant pot of water. Okay, less molecules, less energy, hopefully less damage to you if you get it spilled on you. Okay, so thing about heat transfer to take away from this slide is Mother Nature always goes from high to low. Okay, spontaneously on its own. Okay, in order to go from low to high, we have to put energy into the system because Mother Nature doesn't like that. Okay, so heat or energy goes from a high temperature to a low temperature. So the temperature, that's where the transfer of energy. Think about this for a second. First thing in the morning, you're in there taking a nice hot shower. It's kind of cool outside, cold outside. You're in there taking a nice, you got hot showers, bathroom steamed up. You stepped out of you step out of the shower. What happens? You get cold, right? So you go, whoa, it's cold. So you jump back in the shower. What happens? You warm up again. So what's happening there? Okay, think about this for a moment. You're in the hot shower. Your body now, you've been in there for a few minutes. Now your body temperature is pretty much equated to the temperature of the hot water. Okay. Now you step out of the shower. Now, with respect to the environment, you are higher in temperature and energy than the environment. So the heat on you transfers to the environment. So you get cold because the heat goes away from you and into the environment. So you cool down, you get cold. So what do? You jump back into the hot shower that was there. Now your temperature has dropped. okay, compared to the shower, which still is pretty high temperature. So it transfers its energy back to you, and what? You warm up, okay? Eventually, everything is going to equilibrate. And that's nature. You got a hot cup of coffee, you let it sit on a kitchen table for a period of time. What happens? It loses its heat to the environment, and it temperature goes down, and it equates to the same temperature of its environment, room temperature, whatever that may be. So you're cooking, making some cookies, take them out of the oven. What's going to lose the heat? The cookie as you grab it. And who's going to gain the heat? You are. And if it's too hot, it's going to burn you. Okay. All right. So temperature transfers from a high temperature, high energy state to a low energy state. Okay. Some other examples, you got a piece of metal in the freezer. The metal is then put in a bucket of hot water. Does the temperature of the metal increase, decrease, or remain the same? Well, temperature of the metal increases as it gains heat because it's cold. All right. You got a bucket of hot water, high energy, is going to transfer that heat from the water to that cold spoon. Okay. So what happens is the temperature of water decreases. Why? Because it loses energy, and the heat transfer, because the heat transfers from the water to the metal. So keep that in mind next time you got a very hot cup of coffee and you want to cool it down pretty quick, stick in a cold spoon. Okay. And that heat from the hot cup of coffee or tea or whatever you're drinking is hot will get transferred to the cold spoon, and the temperature of the liquid will drop. Okay. All right. So quiz 1 coming up soon. Okay. So you want to, make sure you study the chapters. Okay. The worksheets. I've been uploading these videos. Okay. So if you don't like this video, which is fine, I don't have a problem with that. Dr. Ken's videos are available, so take a look at those. Okay, don't forget the chapter problems. Be familiar with sig figs. Sig figs are not going to end with this chapter. Sig figs continue throughout the rest of the semester. So, all right. So don't forget the assignments and so forth. Any questions at this point in time about anything that you may have? Because this is the end of chapter 3. Okay. No questions? All right. Well, tomorrow I'll be here from 1 to 2 for office hours. Feel free to drop by if you have any questions. Send me email. I try to get back to you as soon as I can with the answers. So just let me know